Now we're going to build off what we already have established, looking primarily at potassium, knowing sodium's involved. So we're going to add the sodium story in, and we're going to start to look at how this was analyzed using the giant squid axon. I'm also going to add in a little bit more information with what an action potential looks like and how we name different elements or parts of the action potential. So let's start with activity that does not lead us to threshold, right? So here we are looking at the left figure here. We're at that resting membrane potential, that minus 70 millivolts, and we give them some kind of a reaction. Maybe we give them an electrical stimulus or some kind of a reaction on that neuron, and maybe there's repeated ones, right? But the idea is that none of these reach threshold. Because of that, these are called graded potentials. They do not lead to an action potential. Most of the time, this means that there's small activity at the surface of the plasma membrane. So maybe there's only a little sodium that's moving, a little potassium that's moving, but the idea is that all of these sub-threshold events do not lead to action potentials. However, it's important to note, and this is incredibly important, you should write this down, that graded potentials can actually add in summation. So if we have two events that stimulate the same region of the neuron in short succession, it leads to a summation of the two events. And until it reaches threshold, those two events can actually depolarize, get us closer to threshold, but they won't cause the action potential. Action potentials are largely occurring because of the potassium ion concentration. I've mentioned this a couple of times. But there's some interesting things here that I want to note. So on the top graph here, we can see the increasing concentrations of potassium that are going to be inside the cell. Now, across the bottom, if we plot this, we can see the curve going up and up and up. And if we plot this against the Nernst equation for potassium, right, that we saw prior, we can see that these two lines here are very similar when we get to much higher levels of potassium. But lower levels of potassium, we can see that they're not similar. So this line here is very far away from. So what this means, I'm going to tell you right now, is that something else is playing a role. Specifically, that sodium and some of that chloride or calcium are playing a big event at lower concentrations here of potassium. We can see it. When we see much higher levels of potassium, we miss that event. So let's talk about the three different parts of an action potential. So if we reach threshold, right, then those graded potentials are going to lead to an action potential. An action potential is all or none. We always hit positive 35, positive 40 millivolts because once we reach threshold, we must go through the whole process. We're going to stimulate in that region, and it's going to walk down the length of the axon, and it doesn't matter how strong the stimulus is, it's always going to reach the same point, that positive 35, positive 40 millivolts. There are three phases that are typically talked about: the depolarization phase, the repolarization phase, and the after potential. And we will talk a little bit about each of these in more detail in the next slide. So let's focus on what's actually happening chemically during each of these phases. Let's focus first on depolarization. Depolarization is when the inside of the membrane becomes more positive. Okay? This means that sodium is playing a role here because it diffuses into channels from the outside extracellular through these voltage-gated ion channels to the intracellular portion of the neuron. So depolarization is largely a sodium event. And we saw that prior when I showed you that darker orange compared to the lighter yellow events. When we're in resting membrane potential, it's largely a potassium event. But when we're looking at action potentials, it's largely initially that sodium event. Okay? So this depolarization, right, is going to be sodium. Okay? Repolarization is when the sodium channels, those voltage-gated sodium channels, close, but now new voltage-gated channels, namely the voltage-gated potassium channels, actually start to open, and this causes a repolarization event to occur. We go now through and past resting membrane potential, and that's why it's called an after potential. I should note to you in your book and in other parts of the chapters, you're going to see these events occur and they reflect 6 different parts. The first is resting membrane potential. The second is that we reach threshold, then rising phase, an overshoot, a falling phase, and then an undershoot, or that after potential, right? So the video that I've placed online that ties these two together, the key here is that the rising phase, the overshoot, and the falling phase are the action potential. Those are the critical ones. The other ones lead us to and take us away from that actual event that occurs above threshold. Okay. Now these events, rising phase, overshoot, and falling phase, are the same every time, right? That's that all or none response. The only thing that changes is if it's a bigger event, we're going to see more of these happen, more frequent, in a shorter period of time. There's a limit on that. We'll talk about that later on. Now, it's critical to note the undershoot here, the after potential, is because the potassium channels are slow to close and the sodium channels up here in the overshoot are very quick to close. So because the potassium channels close slower, they actually shoot past the resting membrane potential and eventually they close and we come back to that resting membrane potential. Now, it's also important to note that I told you earlier that if we change sodium levels, they have very little effect on resting membrane potential. And that's what you see down here in E. When we change sodium levels on the outside of the cells, it really has very little effect on resting membrane potential. Because remember, potassium is the key player in the resting membrane potential. But when we're looking at action potential, sodium plays a role. So this is a normal control event here. You can see an action potential in A here. And then we come back and we can see that if we change the concentrations to low sodium, we see that the overall amplitude of the action potential drops. Okay. And we can see that here, if we bring the sodium back in C, we get right back to where we were in A. So it looks like sodium plays a role in that depolarization event, just like we would expect. And in D, if we looked at the Nernst equation, we can see that that definitely is what was happening here. The sodium levels are what play a role in those action potentials. It's also important to note that the action potential process, this rising phase, overshoot, falling phase, undershoot phase, these are different when we look at different organisms, okay? So if we look at a frog myelinated neuron, a frog soma, a guinea pig inferior olivary complex, or a Purkinje nerve fiber on a cerebellum of the guinea pig, we can see that there are much differences in what happens in the action potentials. So it should be noted that when we see action potentials in mammalian systems in the body compared to squid, they're very similar. But when we look at other species, the action potential process still works the same. It just happens over a longer time. The amplitudes are higher sometimes, and they might show a slightly different process. Last is looking at anesthesia. This figure is looking at procaine and lidocaine, 2 common anesthetics. And when we look at a normal event here, we can see a normal event, and we add lidocaine, look what happens to the amplitude of the action potentials. They're greatly reduced. In fact, we see the same kind of thing when we look at a control here, and we add in our other anesthetic here. We can see that this greatly moves us in a hyperpolarized way away from threshold.